Hey math fans, Alex here. In the last episode, we counted the number of ways that you could sample a population by replacing the objects after each trial, and the number of ways you could do it without replacing them. So just recall that the number of ways with replacement was little n to the r power, where little n was your population size and r was the number of objects that you were to draw. And if you're sampling without replacement, capital N is going to equal n times n minus 1 times n minus 2 times all the way, and then your last term is going to be n minus r plus 1. Okay, so watch the previous video if you want to see where these come from, but we're going to use these a lot today. Now, there are going to be situations in which we want to know how many ways a group of R objects can be selected from a population of N objects. Okay, so I'm going to write that down and then give you an example. All right, so we'll need to count the number of ways a group of R objects can be selected from a population of N objects. Okay, so the situation is we have some sort of a population N that's filled, and we want to select a group of R of those objects and figure out how many ways we can do that. Okay, so just as a quick example of why this might be needed, and I'm not actually going to solve this example, but we're going to talk about it. So here's a question. Okay, the question is, what's the probability of drawing 5 cards out of a standard deck and having 3 red cards? Okay, so we're going to talk about this a little bit. So remember that probability. So recall that probability is the number of ways that an event A can happen over the total number of ways, capital N. We can kind of fill these out. So let event A be having 3 red cards. From the 5 drawn. Okay, so then the number of ways that can happen is simply number of ways to get 3 red cards from the 5 drawn. And the total number of outcomes, well, you're drawing 5 cards. That's just a fact that the experiment has to go by that. But since there are 52 cards total, capital N, or the total number of outcomes, is just the number of ways to draw 5 cards. And that 5 cards is going to be from a population of 52. So stuff like this, we're going to need some sort of toolbox in order to answer questions like this, which is what we're going to be developing today by defining a combination. But we're going to do it in a theorem. So this is going to be Theorem 1.3, which says the following. A population of N objects, has exactly that number of subpopulations of size R. Okay, so let me just comment about what I mean by subpopulations, and then I'll kind of explain these exclamation points or just have you review that. So imagine again that you have population of n. We define a subpopulation as a group of R objects. And we just want to know how many such subpopulations exist. The important thing, and this is going to be important for the proof, is that the order of elements in a subpopulation does not matter. Okay? Now, just to recall, so a little reminder for you. That this exclamation mark is a factorial. Okay, so that's the factorial symbol. And the factorial symbol means that you take the whole number that you're on and you continuously multiply whole numbers, decreasing by 1 each time until you end up at 1. Because if you were to decrease this by another 1, then you get 0, and then it would be pointless. Okay, so you multiply 6 times 5 times 4 times 3 times 2 times 1. And that's 6 factorial. N factorial, you start at n, and then you take that times n minus 1, then you take that times n minus 2, and then you keep multiplying until you get to 3 times 2, and then finally times 1. Hopefully you understand why I'm introducing this notation to you, because we've seen many situations where we've just had cascading products. We're going to really kind of milk this notation, so to speak. Okay, so let's prove that a population of n objects have exactly that many subpopulations of size r. And we're actually going to use the fact of sampling without replacement that I just reviewed. Okay, so this is going to be an important fact that we use. Okay. Let's prove this. Well, in order to prove this, I'm actually just going to reframe the question. Okay, so when it says subpopulations of size r, what that's saying is, so this is equivalent to asking how many ways are there to pick R objects from a population of n objects. Okay. Well, based on example 3, which is also the sampling without replacement, we already have the answer to this, right? The answer to that is n times n minus 1 times n minus 2 all the way up to n minus r plus 1. Or at least that's close to the right answer. The problem is, when you sample without replacement, the order of elements that you select matters. And we don't want it to matter. Okay? So what we have is we have that this product over here is actually equivalent to two terms. The first one being the number of subpopulations of size r. But the second term is going to be more specific, because this is basically saying that 1, 2, 3 is completely different from 2, 3, 1, which is different from 3, 1, 2, right? So all of those orders matter, which means this is actually bigger than this. So in order to compensate those, in order to establish equality, we have to take the number of subpopulations of size r, and for each subpopulation, for each of these little groups of size r, we have to multiply that times the number of distinct arrangements for the R objects. If we could just figure that out, we're done. Well, how many distinct arrangements are there for R objects? Well, that's not too difficult to figure out. I'll actually just do it in the same color. So for this, assume we have R objects, and we want to just kind of figure out how many ways there are to arrange R objects in R slots. Okay, so then eventually we get to the rth object. Well, if you take R objects and you arrange one of them in the first slot, there are R of them to choose from. Then there's one less to choose from, so the second slot, you have R minus 1 options. The third one, you have R minus 2 options, and so on and so forth until the rth position is the last one, which means you only have one more object that you could possibly put to rearrange it. Okay? But guess what? We have a notation for this now. This is simply R factorial. Okay? This is R factorial. So now we're almost done with the proof. Because we have that, our answer right? Since we're trying to solve for the number of subpopulations, we get that the number of subpopulations size r equals the sampling without replacement divided by R factorial. Okay, and everything I do from this point on is just going to be kind of rearranging this so that it looks like this highlighted portion, which is what we're trying to prove. Okay, so let's see if we can kind of mess around with this. The first thing that I note is that if you think about it, I'm going to multiply the top and the bottom by, let's see. Yeah, I'm going to multiply the top and the bottom by n minus r factorial. Okay. So what does that do? So I can just keep rewriting this, right? Because n times r factorial is n minus r times n minus r minus 1 all the way until times 2 times 1. Okay? And all of that is being divided by r factorial and n minus r factorial. But then finally, I note that this entire numerator is nothing other than n factorial. I take n times n minus 1 all the way down to 1. So this is just simply n factorial divided by r factorial n minus r factorial. And then I'm done. Okay. Now, a couple of comments about notation. because this coefficient is so important, this number is so important, that we actually call it a bunch of different things. Okay, and just remember, this is the number of subpopulations, where the order doesn't matter, the number of subpopulations of size r from a population of size n. So we can notate this a couple of different ways. The book uses this notation with a subscript of r and a superscript of n, where the capital C stands for combination. Okay, a lot of graphing calculators nowadays use this notation, little n, capital C, little r. Okay, or you'll see it in a kind of column vector that says n and r. Usually what people say is they will say n, so out of n, we are choosing r. So if you want to think of the C as instead standing for choose, I wouldn't blame you. Okay? So out of a population of n, I'll just draw this little diagram one more time. Out of population of n, we are choosing r elements, and we are figuring out the number of ways that can be done, where of course the order of the elements in each subpopulation doesn't matter. All right, so the last thing that I wanted to do in this video is end off with an example. Okay, so let's do a quick example. All right, so here's the example. It says a batch of 100 manufactured items is checked by an inspector who examines 10 items selected at random. Quality check. If none of the 10 items is defective, he accepts the entire batch. What's the probability that a batch containing 10 defective items will be accepted? Okay, so the idea is that you have a population consisting of 100 items, and 10 of them are bad, right? 10 of them are defective, and they're kind of interspersed in the 90 that are supposedly good, right? So the question is basically saying that the quality inspector is going to select 10 items at random, so he's going to select a sample size of 10 items. And we want to know the probability that that batch contains no defective items. Okay, so I'm going to go ahead and let the event A be drawing a batch of 10 items with no defects. Or in the language of what we just talked about, we want a subpopulation with 10 good items and 0 bad items. All right? So remember, probability is the number of ways A can occur divided by the total number of outcomes. So how many different ways can that occur? How many different ways can you choose a group of 10 that has all good items? Well, in this population, 90 have no defects and 10 have defects. So we essentially want, out of the 90 items without any defects, we want to choose 10 of them in our sample. All right? So out of the population of 90 good items, we want to choose 10 of them in the sample. Okay, so how many ways can this occur? Well, according to Theorem 1.3, this is just 90 factorial divided by 10 factorial times 90 minus 10 factorial. Okay, which is just 90 factorial divided by 10 factorial, 80 factorial. Okay, and this is by Theorem 1.3. Well, how many total ways are there? Well, we're trying to draw just a sample of 10. How many different ways are there, or how many different subpopulations of 10 items there are in a population of 100? Well, that's 100. Choose 10. Right? Out of 100 total items, we're choosing 10 of them, and we want to know how many different subpopulations that gives us. Well, that is going to be 100 factorial divided by 10 factorial times 100 minus 10 factorial, which is 100 factorial divided by 10 factorial, 90 factorial. Okay. All right, so then we want to combine these two into our formula, right? Because we know that probability of A occurring, number of ways A can occur divided by the total number of outcomes. Okay, so we're going to get 90 factorial divided by 10 factorial, 80 factorial on top. And the denominator is going to be 100 factorial divided by 10 factorial, 90 factorial. Okay, so we kind of have to simplify this fraction. Well, the first thing that I'm going to do to simplify it is cancel out the 10 factorials, right? Those just go away. Then I can actually kind of divide these fractions out by taking the inverse reciprocal. Okay, so we can take this fraction and multiply it times the reciprocal of that function, or of that expression. So we get 90 factorial divided by 100 factorial. Okay, and then it takes some experience to like practice dealing with expressions with factorials. But the idea is this expression right here, this expression right here is really just 90 times 89 times 88 all the way down to 81 times 80 factorial, all divided by 80 factorial. Okay, so these 80 factorials clearly are going to cancel out for the first term. Now the second term is going to be very similar. We're going to have 90 factorial divided by 100 times 99, all the way down to 91 times 90 factorial. Okay, so the 90 factorials are going to cancel. Okay, so after some simplification, we get that this is basically 90 times 89 all the way down to 8 times 81 divided by 100 times 99 all the way down to 91. Okay? Now, this is really going to be an approximation. You can type this in your calculator, no problem. But if you look at this, this fraction is just 9/10. And this fraction is really close to 9/10. And this fraction is also fairly close to 9/10. So if you want, we can kind of approximate this by saying this is about 9/10 to the 10th power, which is equal to 0.349. So the probability is about 35% that we sample 10 good items if 10 out of 100 of them are defective. Or another way of saying that, since we know that 10 over 100 is 10%, if 10% of our items are defective, at least for this particular sample size, there's a 35% chance that we'll accept the batch because there are no defective items. All right, I'm going to go and end here. The next video, we're going to take a look at some formulas involving partitioning a population, and we're going to finish off with some more examples. Thanks so much for watching. Have a good day.